the way soil testing recommendations and the interpretations they were developed traditionally over the past nearly 100 years have been to make sure that there is economic production, the yield increased. Eventually, we came to an era, last 20 years plus, where we have to start thinking about the environment based on what we applied and how much remains back in the soil or in the environment versus what ends up in the yield that we take home. So when that happened, there is a lot of balancing acts that we had to do, and we're still doing that. And if you see this graph here, as you increase the inputs, eventually there will be a point where they'll start stabilizing. You can't increase the yield much. However, if you see what happens is the profit falls. Eventually, what we have come to a point where we've seen the time where the fertilizer prices increased dramatically in the last few years. And then now they get back to kind of more stabilized pattern. But however, during that time, we realized, the profit margin came into being, and then everybody started thinking about, okay, how much should I apply? Previous to that, we didn't really have to think because fertilizer application and the costs were probably not so significant part of the overall cost of production. But if you see this graph, you will see the profit falls much before. Profit in the sense, the return you get for the input, the cost of input, falls much before the yield itself. Soil testing is a 3-step process. What we go through at the lab when the sample arrives is analysis and computation of the results. That's the first step. We analyze based on what was sent, what we see is appropriate. That test will be performed. And then there will be interpretation. Now you get a bunch of data once you put something into the machine, and they are all trained to do that. So you get a lot of information. So what does that information mean? So someone has to interpret, make sense of the data. Then based on how we interpret the results, we come up with a package of recommendations. That recommendations, the way they are developed is by field calibration, not just by interpretation, but then you go back to the field, apply different dosages of different sources, depending on what we're trying to do, and find out where the response is. If there is no response, that means an additional input of fertilizer or any particular nutrient will not be helpful in improving the yield or quality. Also get a representative sample. If that sample is not representative of the area or the issue that you're trying to deal with, then you will be getting an erroneous result. So the result is only as good as the sample is. So the first step, analytical procedures, try to mimic actually what happens in the field, like how the roots uptake. What could be available in the next following 3 to 4 months of that cropping season, how the plants would be able to take up and what could be available from the soil. That's what's done, and that's called extraction procedure. We have a way of extracting those nutrients from the soil, otherwise would have been absorbed or bound to the soil particles. But over time, eventually, due to root action, the acidity around them or other reasons, they could be slowly released and be available to the plants. That's what the soil testing lab does, soil testing procedure does. And then these extracted amounts are calibrated to the crop production. So you got to go out to the field and make sure those things make sense. If for different soils, therefore, different extractions have been developed. So in Florida, unlike say Iowa or Illinois or the Midwest, we have different sets of soils in different nature, in different groupings, chemically and ecologically. So what happens is you cannot apply the same procedure, like I said earlier, on all soils. So you got to know where the soil is coming from first. So what do we have in Florida? At least 3 distinct regions that are inherently different from one another in terms of the chemistry and the physiographic regions. The ecosystem itself is different. Not to speak of all the other ecosystem sensitive, etc., and the springs that we have that have a lot more sensitivity or higher sensitivity to these applied nutrients versus just the regions. So we cannot deal with individuals. So in order to make things work, we can try to generalize over a certain area. So what we end up with, three major regions in Florida. One is acid soils. Everywhere you see out here is generally acid, but that's inherent nature. In this region, in the southeastern United States, most soils are acidic in nature because of the weather pattern we have and the way they have been developed. And then we have another set way down in the South Florida, in the Miami-Dade, Monroe counties, and elsewhere. Not just those, but those are two counties that immediately come to mind because it is predominant in those areas. But these types of soil can exist other places also in locations, localized areas. And these are calcareous soils where the pH is higher, where you can see even here, even though it's supposed to be acidic generally, because the way our geology is, we are sitting on a thin layer of soil underlain by a heavy, thick concretion of calcium carbonate, limestone. So every time this thin surface erodes or goes away, we are actually bringing the calcium carbonate up onto the surface. So if you are walking out here, you could see a white concretion in the soil. What is that? That is actually calcium carbonate in its mainly native form, pretty active, pure. So that's called calcareous. If you go to Miami-Dade, several of you know, we are probably talking about just walking on the white stuff all the way, either concretions or marl, which is like a finer stuff. So in those cases, it's a totally different soil. I mean, I don't even want to call it soil. It's pretty much 80-90% is calcium carbonate. Dr. Yun Kong Lee is here. He's going to be talking a little bit more about that. And then another set of soils we have is around Belglade and south of Okeechobee. That is the organic soils, where again the organic matter could be anywhere from 50 to 90%. Used to be 90, but then as we continued to till and drain those soils, the soil depth kind of decreased. They became shallower, exposing the lime rock underneath. Again, giving out the same response. So what do we use in these three different soils? For acid soils, we use what's called Mehlich 3. We started using that in the last year and a half almost. And what do we get out of that? We get phosphorus, potassium, calcium, magnesium, copper, zinc, manganese. And the ingredients are given in there. One of the things we need to keep in mind in this Mehlich 3 is ammonium fluoride. Then calcareous soils, the other set. We have a specific nutrient reagent that we found to be somewhat calibrated. But let me be very cautious about this. We've been working on this. I've been working with Dr. Yun Kong Lee in the back and a few others trying to figure out what this is. Unfortunately, the way the whole thing was set up was only phosphorus could be calibrated in the field. No other nutrient was found to have any calibration or was found to be providing any response to addition. So there is some issues we can talk in the next half hour, with Dr. Yun Kong Lee. So, however, as far as today, as far as what has been approved in 1998, 97 in that region, what's called this ABDTPA procedure for that, on all soils that have a pH of more than 7.4 or equal. So that's the cutoff point. When the sample arrives at the lab, we look at 7.4 or not. Then we put it on a different set of pattern. But now I'm going to talk a little bit more about this Mehlich 3. That was primarily the way we went when we had Mehlich 1, which was the precursor of this Mehlich 3, which had weak acids in that, or dilute acids, not weak necessarily, it's dilute. And then organic soils. Currently, on those soils, for all sugarcane plantings for phosphorus, we use Mehlich 3. This has been changed in the last year and a half or so again for that group of soils for sugarcane. However, water extraction for phosphorus or for all other crops, and acetic acid for these other nutrients. In addition to others, they also do silicon. Interpretation, like I said, the major reason. That is the sole purpose of soil testing programs around the world. Okay, if we don't know what we are trying to generate, the numbers really don't mean anything. They are pretty much useless. But we got to find out. So who can tell? Whoever is the expert. So we go to those experts, a vegetables person or a row crops person, whoever has been doing the fruits, whoever has been doing that research. But remember, in Florida, we have so many new varieties of plants, particularly landscape types. We don't know what those are necessarily. We don't have enough information. Based on the soil test interpretation, what do? A recommendation may be made. If we think there is enough in the soil that the plant will obtain over the time, there may not be any need, right? So there should not be any recommendation. So it's a maybe, not always. So don't expect to send a sample and then get a recommendation back. The recommendation could be a 0. And then we are relevant because we are generally, genetically inherently acidic region of the world. We tend to be on the acidic side, which may not be always congenial with what the plant will like. It would like a little bit higher. Particularly when it comes to phosphorus, is the most trickiest nutrient in the soil. When it gets applied to the soil, it becomes most trickiest. Then that's where, to make it available, the soil test even started for phosphorus. To let you all know about that. That is, historically it was for soil phosphorus, and its ability, its availability estimation is why a soil test has been even started, not for other nutrients so much. So a pH, at about pH 6 or so, just about that, about 6.5, is where phosphorus will be available, potentially the highest in soil. So if your pH is lower, we're going to ask you to move it up by applying lime. So lime may be recommended depending on the situation and what crop you're growing. Particularly if you're growing an acid-loving plant, you may not need any lime. This is the current interpretation. Did everyone get a copy of this? Yeah, okay. There is this this fact sheet that we have recently published. This took a while to get out, but this is called Extraction of Soil Nutrients Using Mehlich 3 Reagent. This table that you are looking at is from this particular fact sheet. It is table number 4, which is the latest on the Mehlich 3 and the interpretation. What we found was, and like I said, this is not final. As we find more and more information, as we find more field calibration work and data results, we will probably fine tune these. At this time, there used to be very low, there was a very high. We removed those because they don't necessarily mean much for us. So we have phosphorus, potassium, and magnesium interpreted in this way. Every time, say for example, it's more than 45 phosphorus parts per million, which is also called milligrams per kilogram. They are the same. It is considered high. So there is no recommendation. So that's how it goes. I'll just quickly go through these graphs for a minute here. These are the same graph that you see in the in the fact sheet. This is what we use to draw those low, medium. Just so in this graph, if you see, say, take any graph, say between low and medium, those red lines, that whole length of the graph gets the same recommendation. Say, if it is low or medium, the recommendation for phosphate recommendation is 45 pounds per acre. That entire region gets the same 45 pounds, even if you're at the lower end or at the higher end. So in a way, we have a range already inherent or implied in our recommendations. It's not like people say, oh, we need a range of recommendation. We already have that in the recommendation.